Hi ho. So I did the second law of thermodynamics for you. I defined the concept of entropy, which I said was a state variable that is a measure of how disordered our system of particles is. And it helps characterize the system just as much as pressure, temperature, volume, mass, charge, all those things together. It's just another thing that helps you define what your system is. And then I put the finishing touches on the three laws of thermodynamics. The zeroth law: if two states are in equilibrium and two other states are in equilibrium, then the first. Anyway, if system A is in thermal equilibrium with system B is in thermal equilibrium with system C, then systems A and B are in thermal equilibrium with each other. The first law says that the change of internal energy, or thermal energy, as it's also called, the change of thermal energy of a system is exactly equal to the amount of work you do on the system, or is work done by the system, and plus the amount of energy, the amount of heat, I should say, that is transferred into or out of the system. So do work on a system or allow the system to do work, that will cause a change in the thermal energy. Allow heat to flow in, allow heat to flow out. Again, that will change the thermal energy, and the combination of those two things is exactly equal to the net change of thermal energy. That's just conservation of energy applied to a thermodynamic system. And then the third of the three thermodynamic laws, which is called, unfortunately, the second law of thermodynamics, is that the entropy of a system, the entropy of an isolated system can never decrease. It can stay the same. It can increase, but it can never decrease. So, zeroth law, equilibrium is possible. First law, energy is conserved. Second law, the change in entropy of a system is strictly greater than or equal to zero. Okay. As for the entropy, again, conceptually, I defined it as a measure of the disorder of a system, a measure of how random the system is. Mathematically, I said that it is equal to, and I wrote this originally. So if you have n number of particles making up your system, then it would be, you have to add up the change of heat, the flow of heat to or away from each individual particle, and this, when the system is at a given temperature. And I want to clarify this a little bit. We are going to make the assumption that the amount of heat that we gain or lose and the corresponding change of entropy is going to be small enough so that the temperature of the system does not change during the change of entropy, during the heat flow. Okay, this is, of course, only approximately true for physically real particles, but water molecules are so tiny, to use an example, compared to an entire glass of water, that if I look at one water molecule at a time, it can gain or lose kinetic energy, therefore, by gaining or losing heat, without measurably altering the temperature of the entire system of the glass of water. So speeding up or slowing down one single water molecule won't have any effect on the temperature of the glass of water. So that's the implication here. For those of you who are into calculus, the calculus version ends up being that delta S is the integral of dq at a given temperature. And if you understood that, that's great. And if you're not good with calculus, don't worry about this. This will be fine, especially because what I'm going to do with this one is say, well, the summation here, since we're assuming that T is going to be constant, the summation doesn't affect the temperature, and the temperature is not affected by the summation, so I could pull it out. And so we often write it like this. But if I add up all those delta Qs, all those changes in heat, then that's going to be simply the total change of heat for the entire system, which then gives me a nice simple relationship, and that is that how much does the entropy change? It depends on how much the heat changes at a given temperature. And for our purposes, for actually calculating things, that's the one we need. Let me give you a straightforward example of this. Although I will tell you that the example I'm going to do for you, I'm going to throw in, almost by accident, a couple of new additional thermodynamics ideas. So I'll point them out as we go. All right, so let's take a look at an example. And I'll just write it out and then we'll talk about it. I have to look at something here. So let's suppose we have a container with an ideal gas in it. A what? An ideal gas. An ideal gas at 200 degrees C is allowed to expand isothermally. What was that word you used? Isothermally. And when we do this, the gas is going to lose heat. And suppose it loses 8,422 joules in the process. Calculates change of entropy. Now, the actual calculation is pretty trivial. You can see from this equation here, we should be able to just plug in the numbers. But let's walk through this a bit carefully, because, as I suggest, there's going to be some new thermodynamics appearing in all this. You've already seen some words in there. Okay, to start off with, well, step one, let's draw a diagram. All right, so I have an ideal gas. Maybe you know what an ideal gas is, maybe you don't. I will explain it here in a moment. At least I'll give you the overview of what an ideal gas is. But let's not worry about the adjective. It's a gas. I have a container of gas, and it's at some temperature. Okay, so let me draw a container of gas. I don't know. I'll draw a can. Actually, my can a little bit shorter. And actually, I'm going to do something clever, which you probably, there's no reason you would have thought of doing this yourself, making this drawing yourself, or doing this in your drawing. In fact, I'm going to do something even better. Let's see, here we are. And I'll explain this in just a moment. No, I'm not drawing a battery. I think I should have done this. Okay. And here's my gas. this point, I'm not going to care what kind of a gas it is. It's not relevant as long as it's an ideal gas, whatever that means. Okay. What I've attempted to draw here, let me zoom in on it for you a little bit. All right, so what I imagine I have drawn is a big surrounding canister, a circular can of some sort, and then inside of it, drawn in brown here, is meant to be a second snug fitting can, which is actually going to hold, which is actually holding our gas. That's the red stuff here. And then there's a lid on this, and the lid is, I imagine that I'm able to move it up and down, this brown lid, and we'll assume that I can move it without friction, so I don't have to worry about energy loss to friction. Okay. And so in my next drawing, this is our initial state, and then the problem says that the gas is going to expand, so I'm going to draw my same sort of surrounding can, which is just there to hold things in place. And I'm going to, since we're allowing the gas to expand, that means that my little lid here is up higher now. And so our gas, obviously the amount of gas that we have hasn't changed, but it's got more room to spread out in. And so it will spread out. Okay. And less density, less dense now. Okay. And so, yeah, so this has been our change of volume. It went from that volume to that volume. Okay. And so that's our situation. Yeah, let's kind of walk our way, think our way through this. I'm going to pause the recording for a moment. Somebody's coming in the room. Okay, sorry about that. Interruption. Right, so that's the physics that's going on. Now let's kind of walk our way through these things and let me show you some new ideas. Okay, so first of all, ideal gas. Now there's a very formal definition of ideal gas, and we will talk about it in another recording. But for the time being, I'm going to partly assume that you've heard it before somewhere in a chemistry class or something. And so I'm just going to touch on the high points that I need here. And the essential idea is a gas is ideal if I don't have to care what the gas is made of, is the essential idea. That the behavior of the gas is going to be well described by these three laws of thermodynamics with the various equations that you may have heard of, Boyle's law and Charles' law and the ideal gas law and so on, that all those equations actually apply. A little more detail, probably the most crucial idea in a gas being an ideal gas is something that I've been ignoring, and for good reasons, as you'll see in a moment. I've been ignoring the possibility that as the particles wander around and collide with each other and so on, I've been ignoring the possibility that the particles exert forces on each other other than the direct forces of collision. In other words, after all, they're all charged particles, for example. Shouldn't they be exerting electric forces on each other? The answer is yes, they do. That said, that first of all, the electric forces tend to be, among gases, tend to be pretty darn weak compared to the collisional forces. So in a lot of cases, we can, to a good approximation, we can ignore them. We can't always ignore them, and the less ideal the gas is, the less correct we will be by ignoring those so-called internal forces, those electric forces. So one part of the definition of an ideal gas is that the particles do not interact with each other at all. That is to say, they don't apply any forces on each other at all other than the direct forces of collision. And so that's good enough for my present purposes. So we'll assume that that's the case for whatever gas we're working with. And one consequence, as I suggested a moment ago, if the gas is ideal, that means I don't have to care what kind of a gas it is because it doesn't change its behavior. So that's why I'm not saying this is hydrogen or neon or anything else like that. It's an ideal gas. Okay, and it's at 200 degrees Celsius. course, we're going to have to convert that to Kelvin to make our equations work, so we'll be careful of that. We're expanding the thing. In other words, we're increasing the volume, so I've indicated that. And then isothermally, there's a new word. Okay. Isothermally, we can break this down. Well, you see therm or thermal, so that refers apparently to heat or to temperature. And iso is the same root as the beginning of the word isolated, right? And in this context, what it's suggesting is by itself or its own or just a single thing. And so what the word isothermally here means is at a single temperature. So what that's suggesting here is that as this gas expands, the temperature of the gas does not change. Now, how do we perform that magic? The typical physical way you have to do it is when you increase this volume, you have to increase the volume very, very slowly. And that gives the gas time to transfer energy around so that every part of the system stays in thermal equilibrium with every other part of the system, zeroth law of thermodynamics. And so we can change the volume, change the number of possible places that the particles can be without affecting the temperature. So isothermally, one temperature. All right. So that's what that means. And then, okay, so we're going to release that many joules of heat. At this moment, we don't know any good reason to say that it lost heat rather than gaining heat, but the fact is it's going to lose heat. Okay, and again, you may have studied that in some chemistry class or other, where you know that if you increase the volume of something, you drop its temperature, and that's true here, and that's what I'm relying on here. But if you've never heard that before, then just take my word for it that happens to be the case. All right, so the temperature doesn't change, but the amount of energy does change. Okay, so evidently, remember the first law of thermodynamics is not just work, but it's also heat. Okay, so the change in internal energy, the change in the thermal energy system, does not depend just on the heat, but it also depends on the work done. So evidently, work is happening here to offset the change in heat. Okay. All right, so we lose that much heat, and so how much did its entropy? How much did its entropy change is, I guess, what I really meant here. All right, with all those ideas sorted, I think we can tackle it now, because as I say, the actual calculation is pretty darn simple. So we don't need a coordinate system here, so we'll just skip to solve. And this is just plug and chug now. The change in entropy is simply the amount by which the temperature changed divided by the constant temperature at which we are requiring or saying that the system will stay at. Okay, and so delta Q is 8422 joules. Oh, no, it isn't. It's negative 8422. Okay. I'm sorry. That's incorrect. Okay, I need to clear that up. Hi. Yeah, I just had a little Friday afternoon mess up in my head. Let me clarify a couple of things. Okay, so I was worrying about the sign here of the heat flow of delta Q, and I said something that was, to be kind to myself, let me say it was misleading. So let me be a little bit careful. So let's go back. So we're going to increase the volume of our gas container here, and so as we do so, as I say, the volume increases. Okay, and ordinarily the temperature would decrease as a result. However, I've said, in the statement of the problem says that it happens isothermally, meaning the temperature does not change. Okay, and so how could it be possible to increase the volume without changing the temperature? And the answer can only be if heat flows into the system. And I think I mistakenly was saying that heat was flowing out of the system, and that's absolutely incorrect. Sorry, heat was flowing into the system. So ordinarily the temperature would decrease because of the volume expansion, but because we're requiring that the temperature not change, then the only way to satisfy that is for heat to flow into the system. So delta Q goes in, and that makes delta Q a positive value. Okay, so my mistake there. So I apologize. But the rest of it is pretty easy. And by the way, this actually sets a lesson. First of all, let me just go ahead and complete the problem. So we're going to convert the 200 degrees 200 degrees Celsius into Kelvin, and remember that the Celsius scale and the Kelvin scale are offset from each other by 273.15 Kelvin, and so you convert that by simply adding in the zero offset, and you plug in those numbers. And looking at my computer screen, I got 17.8. There we are. 17.8 joules per Kelvin of entropy change. And it's a positive change. And let's see if that makes sense. Okay. An increase in entropy, which is suggested by the fact that this number is positive, an increase in entropy suggests that the system is more random now after the expansion than it was before. And I hope it's clear that that's true, but let me say a couple of things, kind of hammer the point home. One way to measure or describe the amount of disorder in a system, the amount of randomness in a system, the amount of entropy in a system, is to ask how many possible locations or combinations of locations can the gas particles take on? Well, taking it simplistically, having increased the volume, I've increased the number of places where the particles could be, thus increasing the number of possible arrangements of the gas particles. I haven't increased the number of gas particles, but I've increased the number of places where they could be, and that is, as I was doing earlier, a measure of the disorder of the system. Okay, so we expect that, and in fact, I was going to say that it was that expectation that the entropy increase, which clued me in that I had done something wrong with my sign on my delta Q. I knew that delta S had to be positive because physically the entropy is going to increase in this process. But by slapping what turned out to be an incorrect negative sign on delta Q, obviously my delta S was going to come out with a negative sign. I knew that had to be wrong, so I had to go figure out what was going on fixing it. And here's a lesson to take home from this recording. You'll notice that the entire problem, the actual calculation, which was this equation here, if I had been thoughtless about it, I could have solved this problem in 30 seconds, just plug and chug. I would have come up with a number, and I would have had no idea what that number meant physically. I would have just had a number, okay? Which, yay, the homework, Mastering Physics or Wiley Plus or Moodle or whatever your homework, online homework system is, it would have accepted the number, so it would have patted you on the head and said, congratulations, you got the problem right. But did you understand anything? Maybe not. I spent 20 minutes on this problem, and 19 and a half minutes of the problem was spent understanding the physics, okay? So there's a lesson to be learned there somewhere. All right. So this is the idea of entropy. This is how you think about entropy. And again, the reason, by the way, and I don't want to get lost in things, the second law of thermodynamics, am I lying to you? The second law of thermodynamics says that the entropy can never increase, and yet it manifestly did decrease. And no, that's not what the second law says. The second law says that delta S must be greater than or equal to 0 of an isolated system. If my system is not isolated, then all bets are off. Remember, an isolated system is one that neither matter nor energy can either enter or leave the system. But clearly, although matter didn't leave the system, clearly energy did enter the system. How did it happen? By my reaching in, grabbing hold of the lid, and pulling. Okay, that allowed the molecules to expand. They moved upward. They moved outward, forced through a distance. That was work. Energy flowed in. Clearly not an isolated system, and so the second law of thermodynamics doesn't apply here. Okay, so there's that. I think maybe we better start talking. I think we better start talking about gases in some detail. So either that'll be the next lecture or it's coming very soon.